Hello, everyone, and thank you for attending today's webinar, How to Analyze Multi-Phase Samples with CompoMaps and Spectrum Libraries. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or if we run out of time, you'll receive an answer later via email. We do capture all questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of this webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce myself. I'm Tara Nilese, Applications Manager here at EDAX in Mahwah, New Jersey. I'm super happy to see a really nice attendance with a lot of people from a variety of industries, but most notably a lot of geological people logging on today. So we have some engaging samples for you. Thank you. I'd like to start today's session by exploring the inquisitive nature of our scientific minds a little bit more deeply. So our natural personalities as scientists lead us to have a bright scientific curiosity. And as microscopists, we often look at materials, we magnify them, and we try to figure out what is it. And then as a microanalyst, we take things one step further, a little bit deeper, and we say, what is it made out of? So really what we're doing as microscopists and microanalysts is looking at the small picture to learn about the world around us in the shape of the big picture. And so for a first example, I'd like to have a little fun first, and I'd like to have all of you take a look at what you see in front of you. What we're doing is looking at the fine details of something. And you might look at it and you say it might be a freshly painted wall that's maybe not so smooth, or some stucco. If you're like me, you might say that looks like it could be cupcake frosting. Or you might say that is something that's part of a bigger picture. And if we start to zoom out of the fine details and look at the bigger picture of the world around us, then our perspective might change. And now we realize that we're looking at a beautiful painting, which is the work of a great master of his art. And so this is Starry Sky. And my point here is that as microanalysts, we look at things with the perspective of a really fine, detailed view. But we're doing this in order to truly understand the world around us in the form of the big picture. And when we do understand the fine details, and when we understand the context of those fine details into the big picture, we're able to solve our scientific problems. So let's get started with a little bit more relevant example for microscopy and microanalysis. This is a simple spectrum, and I'd like for all of you to take a look at it, and I'm going to ask you, what is it? And this is going to be the first of our polls today, the first and only poll today. But the peak labels there are oxygen on the left and silicon on the right. And I'd like for you in different fields of scientists and different fields of science and different types of work and industry and academia to think about how you might look at that spectra and think about what it is. So you might say it is silicon and oxygen X-ray peaks. You might say it's the composition of quarks. So if you're a geologist, that might be your perspective. You might also say that silicon and oxygen are the main components of glass. You could say that this is one of the phases in your geological specimen map. You might say all of the above. And there are many different ways of answering this question. You might even say, well, that is the piece of contaminant that I found on my microelectronic circuit, something that doesn't belong there. If you're a failure analysis, you might say this is something, the spectrum that I got from the thing that doesn't belong there. What is it? So if you could take a moment to select one answer And please note that you have all of the options there, including the bottom. We've got a bunch of options for you. And then just click on your answer and then the Submit button. I will give you all a moment, and we'll see how the results turn out in the next slide in just a moment. Okay. So this is great. I love this cross-section of answers. This does illustrate that we have many different perspectives. Truly, factually, it is what it is silicon and oxygen X-ray spectrum peaks. And if you gave that answer, then your perspective is a factual scientist, and you're looking at exactly what's in there. In fact, that might be the answer that I would lean towards. My experience probably tells me that it's the composition of quartz, just based on having seen this a number of times in various applications. And we would also be right if we said these are the main components of glass. Of course, if we had a phase map in front of us, we would also be correct in saying it's one of the phases of a geological specimen. So many different ways of answering this question, and all answers are in fact correct. So any of you that answered all of the above, you are also correct. There are only winners here today. So now where I'm going with this, and just as it might have become very obvious where I was going with it on the image or the painting that we saw earlier, it might become a little bit more obvious where I'm going with this all now. When we looked at that silicon-oxygen spectrum, we determined that some of the answers are, well, that is the composition of quartz, and those are the main components of glass. And so today's topic is CompoMaps. And I'd like to highlight the words composition and components, and also even the word compound, because these are all of the ways that we as investigative scientists look at our materials. So we take our silicon and oxygen peaks and we come up with a composition. In today's session, I'll start with a brief description of what CompoMaps are. And then I'll use some examples and illustrate how and why to collect CompoMaps with some tricks and tools on how to. And then we'll go a little bit deeper and review when and why to use spectral libraries. And finally, we'll go through how to use some of the advanced capabilities of the spectral library matching. Altogether, we'll end up with solutions with the combined power of CompoMaps and spectrum library matching. So the first question is, what are CompoMaps? They are a sophisticated software routine, and they result in a display of each pixel's elemental composition. Really, there's a powerful software algorithm going on behind the scenes, and the result is that it puts our pixel display in a concentration that's viewable for all pixels in a single field of view for a single element at a time. And so a lot of work going on. Each pixel has this algorithm working at each pixel with a display of the results. There are several different types of display results. The first one and the easiest is the net intensity display. And when we say net intensity mapping, we also mean that we're doing a background subtraction, or we're removing the peak from the background, and we're also doing a peak deconvolution. And what that is ideal for is when you have overlapping peaks, and also when you have low signal. So if your peak is just very small above the background, it's much more beneficial for us to be able to remove the background, remove all of that noise, and focus on just those pixels that contain the low peak signal from the element of interest. Now, we all have overlapping peaks in the world of EDS analysis. There are many examples. Today, we'll explore a couple of examples, but some of the common ones are silicon and tantalum, silicon and tungsten, lead and sulfur, lead and molybdenum, and the ones that we'll explore today are some geological ones that really cause us some grief sometime, like phosphorus and zirconium, and a few other displays. So we take it a little bit further now, and all of this math that's going on at each pixel is also being done with a full ZAF correction at each pixel in the map set. And if you think about it, a 256 by 200 pixel resolution image actually has 51,000 pixels in it. And so all of that map going on just a few seconds per frame is a really powerful capability. When we look at the weight percent, we're looking at a favor of the display of heavier elements and major constituents. So weight percent we could think of as higher atomic number. They take up the bulk of the material in the sample by weight percent. Now, if we were to look at an atomic percent map, which is another one of the options available to us in the CompoMaps, those are going to favor the display of lower atomic number elements. Elements like carbon, oxygen, nitrogen, because they don't provide a whole lot of weight percent contribution, these are the lower atomic mass elements, they are going to be underrepresented in the weight percent map. But when we look at them in compound formula, then they provide a more equal display of their contribution into the map display. So what is CompoMaps? They are an in-depth display of the true chemical compound of our elements and our materials within the sample. Each pixel displays a wealth of information. So here are some tools for how to use CompoMaps. CompoMaps is a built-in mapping function, and so when we're in mapping mode, we have a few of our common options available to us, like drift correction and also the ability to assign element colors to our elements while we're mapping. And then you can see here that we also have the ability to do the net deconvolution and background subtraction in live mode. And we also have the ability to do a full ZAF weight percent or atomic percent correction as well. And we can rebuild the maps as we see here in this display. So a few different tools available to us to make sure that we accomplish what we need to. Also available to us in mapping is full control of the spectrum images, the overlays, and the quantitative analysis. So again, back to our inquisitive nature as scientists, we like to explore our sample. So we really can't help ourselves by maybe say pulling a spectrum out of a certain phase, or when we see a bright spot, we want to know what it is. And the tools available to us allow us to extract that spectrum, look at the intensity levels with a scale bar next to the image. We could do a full quantitative analysis. We could add and remove elements, and we could also do a quant display of each pixel in the map set. So quite a few options available to us. And in the first brief example, we're going to look at the visible difference in a CompoMap for a simple overlapping element. We look at a geological compound where we have phosphorus and zirconium, and they look exactly the same to me. If we look at some of the intensities, we might see this cubic area of zirconium on kind of the top center of the map that is maybe a little bit brighter in the zirconium map and a little bit less intense in the phosphorus ROI map. And ROI is a region of interest, so it's looking at the entire peak. When we move one step further, even during collection, and go into live net mapping, so during the map collection, we're actually able to separate out those elements with deconvolution, and sure enough, we see that cubic area or rectangular area in the zirconium map is clearly zirconium and not present at all in the phosphorus map, and then we see other areas that are common to phosphorus only with no trace of their zirconium. So fully separated out between these overlapping peaks, and we'll investigate those a little bit more when we get deeper into the sample. I always like to do an overlay of the two so you can really accurately compare the difference and confirm where they are. Now, recently, a user from a prominent university made what I thought was a great comment, and he said, when I was looking at the ROI maps, those compounds didn't make any sense at all. And for those of you in the field of geology out there, and there were a bunch of you attending today, thank you, you probably agree. Phosphorus and zirconium probably do not make sense in a compound together. And so when we do this full deconvolution, sure enough, we could do the overlay and confirm it's either or, not in combination. Now let's get a little bit more complex with our data interpretation. And we'll start looking at a weight % map of tungsten carbide. And now this is one of my favorite examples, partly because it's such an extreme example. We've got tungsten carbide, which is one tungsten atom and one carbon atom. And so by formula, it's tungsten, carbon, 1-to-1. But by weight %, poor carbon only has 6% of the weight display, and tungsten has 94% of the weight display. And so in the weight % map, really we can't see any of that base carbon from the background. The only place we actually see carbon is in those pores there that seem to have gathered some carbon in them. But otherwise, we see very little display of the carbon in the base material that's common with the tungsten. We know it's tungsten carbide. We know there should be carbon in there, but this particular display doesn't show us the presence of carbon. By weight, it's about 1/15 of tungsten. But let's move along to atomic maps. And now when we map atomically, remember it's going to each and every pixel and doing the calculation, looking at the net intensity, and then doing the ZAF correction and coming up with the atomic percentage. Because tungsten carbide is 1-to-1, it's 50-50, and now our display of carbon and tungsten are equal to each other. So they have equal color intensities. These are just truly tungsten carbide, but you can imagine for a great number of materials we can have fine variations in them as well, and that's the example that we'll start moving on to. But tungsten carbide is just a great example of by weight % we don't see the carbon, it's underrepresented, but when we move on to atomic %, take advantage of all the tools, we could see the accurate display of the compound nature of tungsten carbide. So now let's move on to our multi-phase sample, which is the key of this webinar. And here we'll go step by step through a process of how we can conclude what is present in the sample, what each phase is, and how they relate to each other. So this is a multi-phase material as witnessed by the nice backscatter image showing the variations in gray level. And most all of us microscopists know that you have your backscatter detector to give you a quick rough idea of the variations in atomic number. What we also see is the sum spectrum. And so this spectrum was gathered from the entire field of analysis. You could think of it as a master element list where we sum each and every pixel's spectrum together, and then we identify each and every peak. And when we do this, we combine all the peaks together. Now, all of those peaks together really don't make much sense at all because we have, well, quite a bit of elements there. Not necessarily all in combination, but it gives us a quick view of what we might expect in our sample. And this was collected in just a few seconds. So these days with detectors, the speed of detectors, we could usually collect, I don't know, around 10 or 20 seconds is my normal spectrum collection time. And we could even see the small peaks. So now let's break it down a little bit further. And when we break it down further, we're gathering the spectrum from the various phases in the backscatter image. And this is where we're just using quick and dirty to say, okay, let me get a spectrum, 5 seconds at each of the different gray levels that we see available to us. And this provides a different view of the overall composition. Now we could see that each individual spectrum is not quite as complex. We don't have all elements in each spectrum. We just seem to have spectra with a few, 2 or 3 peaks in each one of them. And note this sample is carbon coded, so that's usually always going to be in there. And for some of you geologists, you're probably already starting to look at some of the overlaps that you might see. And the key there is that we're looking at site-specific chemical information from each of the different areas. Now we'll look at the sample and the spectrum in a slightly different view. So we've gone back to viewing just one single spectrum view, but what we've done is we've taken those individual and site-specific spectra and we've now overlaid them. And you can see various peaks of various intensities. It's similar to the sum spectrum because we have all the elements back in the list, but now they make a little bit more sense. We have like silicon and oxygen, we've got iron and sulfur, and various combinations. What we have now is the benefit of looking at what elements are combined together, and we start getting an idea of what the compounds are together. And then we look at one of the elements that's present in multiple phases. And we could see here in the iron spectra, or in the combined spectra, we have iron at various intensities. And then if we look at them a little bit more, we could see where they decrease compared to one to the other, and they also are present with different elements. So let's break those out now and look at those spectra individually. And we could see now several different combinations of iron and various elements in our material, iron and titanium, iron and sulfur, and so on. So we suspect that we have several compounds, but we really need to investigate further to really understand that they are, in fact, different. And great application for quantitative analysis. With a quick click, we're able to get not just the concentration numbers, the actual weight percent and atomic percent values, but we can also get a nice display of the concentrations. And I really love this display because, as you know, a spectrum peak height is not necessarily indicative of the concentration. And so sometimes you might have a spectrum peak that's more intense than another, but the concentration might actually be lower than another. And that's because of various factors like your ionization, your kV, your overvoltage, all of the things that you learn about in an EDS training class. But the key is that you really can't interpret a spectrum based on peak intensity alone. You have to do those matrix corrections, those ZAF corrections, to be able to really understand the true nature of the material. So when we do this, we can say pull out the two phases of interest here are pointed to, the arrows are pointing to the two phases of interest. We get those spectrum, we get the quant numbers, we see the values, and then we get the bar graphs. We also have pie charts and 3D pie charts too, so whichever way of interpretation you'd like to use, that's available. And then just for ease, I put the weight percent for each of the two phases that we're investigating here down at the bottom. So weight percent, this phase here, 60 and 46 by weight and atomic, and here 40 and 22 by weight and atomic. And now we'll translate all of that chemical and concentration information into a visible display. And this visible display is the weight percent and the atomic percent maps of iron. So we're looking at each pixel displaying the weight percent of iron or the atomic percent. And so on the left is the weight percent, and on the right is the atomic percent. And I've changed the numbers around now. So on the left-hand side, we're looking at weight percent only, and the right-hand side, we're looking at atomic percent only. These are for each of the two different phases, and this will maybe make it a little bit clearer. So we're looking at our two main grains here, and the one on the left has a 60% weight, and the one on the right has a 40% by weight. And we can see on the atomic percent maps that changes a bit. So by atomic percent, the iron is actually about twice as intense atomic percent compared to the grain on the right. But of course, you're all probably looking at that and saying, well, how on earth can you really, how could you really tell by the display? You know, that display, sure, the one on the grain looks more intense, but is that really 1.5%? Like, you know, we say, what is it? It's a nice image. It's helpful to know. We can correlate the spectrum. But the important thing is that we're actually matching the concentration results behind the scenes through the powerful routine with the display that we see in front of us. And so now we bring in spectrum libraries because sometimes just the displays aren't good enough. And so we can have our spectrum analysis, we could see our peaks, we could do a quant and understand what our concentrations by weight or atomic percent are. And we could also visualize with the map data, which is a nice looking image and gives us a good overall view. And we know what peaks are there, we know how much there are, we know where they're located, but truly we want to figure out what really is it. You know, we look at that grain and we want to know what it is. And so then we start to use our spectrum library. So for starters, we pull up the spectrum matching capability, which has a few options available to us. We've got a search function, we've got the ability to load a library, and we've got ability to search and refine. So in this case, we'll use a mineral library and search against it. We'll click on the match button, and that yields a result that shows a spectrum overlay. So the red spectrum was the spectrum from the grain that we're looking at, and the various overlay spectra show the 3 top matches on that material. And then if we look a little bit closer, the top match is 84% of FeS2, which is also pyrite. And so now we know more conclusively what our material is based on the match against a known mineral in our mineral library. The mineral library and the spectrum libraries have 2 different options available to fine-tune your analysis for specifically the conditions that you're working under. The first method is the chi-square on spectrum. And this is really a simple method, which is comparing the spectral fingerprints, really the spectrum peaks. This is great when you have some unknown materials or artifacts. You don't need to depend on peak ID for the spectrum match capability. It's simply matching each channel of the spectrum, each peak intensity of the unknown to every single channel of every spectrum in the library. So really, again, a lot of data processing going on there, but it's great because even if you have some, your carbon coding on your unknown sample versus your standard or so on, those variations are okay. Moving on, there's a more sophisticated algorithm, and that's the chi-square on the concentration results of our spectrum. This is where we take our unknown spectrum and we click on the match button. What it's doing is behind the scenes, it's calculating the weight percent and atomic percent calculations, and then it's using those concentrations to fit against all of the concentrations of all of the materials in the library. And so this is now comparing the actual corrected results, and it's great because it opens up the ability to use it even under different conditions. So for example, if, this map I think I collected at 20 kV and maybe what I compared it to was 15 kV, and we still come up with a great 84% fit. That's really conclusive for pyrite, and it shows that it has that great match. Now keep in mind the sample, the unknown material that I'm analyzing also is carbon coded too. So a bunch of variables in there, but still clicking on the match button gives the conclusive solution of pyrite. Very helpful for us. In the analysis of the second grain that we're looking at in the CompoMap, I'm going to use a slightly different approach. And this is a really nice approach when you know your elements and you want to really hone in on what specific materials might be, or what particular solutions are comprised of those materials. So what we do is we gather our spectrum and then we reference our composition. We look at the weight percent or the atomic percent of those grains, and we see those here in both number and bar chart. Then we pull up our spectrum search and match library function, and we could filter based on several parameters such as filter by conditions like kV, or filter by date, or filter by element. So we can actually search the entire system that you have all of your spectrum on. So if you have vast amounts of data over the years, you could search through all of your data and edit in some search criteria. In this case, I entered in the major constituents, which are iron, titanium, and oxygen. And I even gave it some min and max values by weight percent. And we could see in the green area there, we've got weight percent, atomic percent, or net intensity. And then I've added some values, and I think I did plus or minus 10% to give some larger boundaries for the search. We could also leave those as 0 to 100, and we could add as many or as few elements as we'd like. You don't have to have all of them in there. And then we search for a match. And then this comes up with a matching spectrum that contains iron, titanium, and oxygen with those elements. You could also see there are other elements in there. And this concludes that it's our ilmenite. The really cool thing about this particular one, so this is totally real-world sample. I collected this from this geological specimen a few weeks ago, and then I actually received the spectrum from my colleague in our Utah lab, and he provided this. This was from a work that he did at the M&M conference last year. So truly when we search, we're searching based off a vast amount of data. It doesn't have to be our own system, doesn't have to be our own conditions, doesn't have to be the same detector at all. We could have flexibility with whether it's a different detector, older generation detector, a newer detector, whatever it is, we can come up with these matches based on this criteria. So truly powerful to help us solve our question of what is it. And just a little note on the EDAX Smart Minerals library. This library is created from the SPI 53 Minerals Microanalysis Standard, and you can see that here. This is a great handy sample that we keep around the lab, and we've had it for a bunch of time. Very helpful to have such a standard, and we also bring it to you in the form of the spectral library. So if you don't have the standard, you can also use just the EDAX spectral library on top of it. Also, any of the libraries has the ability to be edited. You could add, edit any library and grow it as large and customize it as much as you would like. So to summarize this aspect of the work, we have found our solution with CompoMaps and Spectrum Library when we combine them together. So at the most basic level, we learned the chemistry of the material with spectral analysis. And we do a composition with our quant results, and then we view those compositional variations with the CompoMaps. That's like doing the chemistry and the image all at the same time, which is why also you might hear the word chemical imaging. That's sometimes used to describe when we do the composition and the mapping at the same time. It could also be called chemical imaging. And then we moved on to fully solve the sample unknown material and grain by comparing against the spectrum library and match against a known mineral standard. And we say this grain is our pyrite grain, this grain on the right-hand side is our ilmenite grain, and that gives our definitive determination of what we have in the material. But we're not done yet. So, just a reminder, if you'd like to type in your question, we're moving along here to a little bit different display. So if you have a question on any of that early work, then feel free to enter it now. We'll get to it at the end. So as we started off, we said we could better understand our components, our chemistry, and the compounds present. And now I'd like to use a different aspect of the sample to differentiate between overlapping elements in the material. So back to the same field of view again, and back to the same sum spectrum. So again, multi-field area. Some of those gray levels really kind of look similar, don't they? You can see several gray areas, gray levels. Might lead you to believe that anything that's the same gray level is the same composition. Not always so. The other thing that you might notice is that in your sum spectrum, you have a few different peaks, and if we really zoom in on them, we could see that one of those peaks there, I have two labels on it, and that's because in the sum spectrum, both zirconium and phosphorus are possibly there. And so both labels are there. We can actually see the deconvolution works pretty well. And that sulfur peak, as sulfur alone, is looking pretty good. So we know there's no lead in there or molybdenum that might be overlapping. So let's investigate our phosphorus and zirconium overlap a little bit more. And here's where we can use our peak deconvolution routine to illustrate what the peak should look like if it was that element only, or if it's that element in combination. And all the way on the left here, we label it as phosphorus only. We say, okay, if this was just phosphorus, how does that fit? And the deconvolution is illustrated in the blue line that's overlapping on top of the red spectrum. And you can see that that blue line doesn't really fit all that well. The phosphorus K alpha should have the alpha and beta peaks, and while they are kind of clustered together in a high energy shoulder, they're not quite two peaks as we would expect for this particular detector resolution. And that deconvolution is dynamic in that it reads the actual detector resolution and it calculates what the peaks should look like. So phosphorus K alpha should have major and minor, alpha and beta peaks at this resolution and this KB, but that peak doesn't. So, okay, so we know it's not just phosphorus, and then if we try to model it as zirconium only, then we say, okay, well that fits the high energy shoulder a little bit better, which makes sense that zirconium, that those L lines could have a nice sequential series of lines together. But look, it missed to the left-hand side of that peak, didn't quite get all of it. So then now moving all the way to the right-hand side, we could see the model of both phosphorus K peaks and zirconium L peaks all together, and that model really seems to have gotten it great altogether. Again, confusing because in a geological material, would we actually have phosphorus and zirconium? So let's use our CompoMaps to help answer that question. We look at the visualization of just the simple region of interest map, and sure enough, it looks like those elements are exactly the same. Maybe the intensities of the grains are a little bit different. The grain over on the right-hand side looks like it's more intense in the zirconium line and in the zirconium map. And some of the phosphorus look more intense in the certain areas on the lower left-hand side. I'll also make note, you can do some image enhancement. So if you really wanted to scale those out, you could probably just strip out the lower intensity gray areas, but that's not really the way to solve a scientific problem. We don't want to do image enhancement to solve our problems. We actually want to investigate the chemistry and understand it further. So now I move on to the CompoMap capability, where this is the truly deconvoluted phosphorus and zirconium peaks. And so I'll just toggle back and forth. This was the raw map, and even while we're collecting, we can deconvolute those two overlapping elements. And sure enough, we see really great separation of those two elements. And now when we look at it all combined together, we see that the two element maps on the left-hand side are in separate areas. We overlay them, and we could even overlay them on top of the image. That gives us a better visual about where the grade level and the correlations are all together, and also some nice topographical information. There are a few divots in the sample, and we could see that with our CPS map, not shown, but a good feature to use to describe the topography of a sample. And now when we look at it, we could visualize the spectra. We see the spectrum from the green areas and the spectrum from the peach or orange areas, and we can overlay those spectra. And sure enough, look at that nice peak difference between the phosphorus peak and the zirconium peak right in the middle there. They are truly different shapes and slightly different intensities. The deconvolution routine is following along the whole time. And again, thinking about, this one was a 512 map by 400, so about 200,000 pixels there, and it's doing all of this math on each pixel for the true display of our compound makeup. So now moving into the most advanced of our investigative tools available to us, if we were to say, okay, well, great, I see that phosphorus area, I want to explore it even further. So now we take the phosphorus map and we use the scale bar here. And so the phosphorus display is a display of the intensity or the concentration, whichever one you have selected. And the display is great, but my eyeballs can't really tell the difference between 20% and 30% on our pixel display. When you do have a quant map, you have a scaling of 0 to 100 weight percent or atomic percent, but our eyes really can't tell those differences. So let's use the histogram slider to select those color levels either by visual intensity or by scalar intensity. And so in this case, we're looking at the net intensity map, and we select the intensity of that area. It'll highlight it on the map, and then we click on the button on the histogram slider, and it extracts the spectrum from each pixel of that's colored, that's selected. So really it's grabbing a color intensity that's representing a concentration, and then it's extracting or harvesting just those pixels. Now, I could draw a box or like a freehand draw. I could try to draw that grain, but my hand drawing is not so good. So when I use this function, we're actually pulling out the data from every pixel there. The result is this spectrum, which acts as a true spectrum. So even though it's harvested from each of those pixels in the map set and combined together, it's truly a spectrum that we could do a quantitative analysis of. We could get our numbers, we could analyze further. And I was really happy to see this fluorine peak here, because this is, this was a pretty quick map collection, a high resolution map, and fluorine is a pretty challenging low energy material. But we have this nice healthy fluorine peak there, as well as the clear fluorine concentration displayed for us. So now we then, if you haven't guessed already, we then use that spectrum, and we use our spectrum library again, our mineral library, and we match it against it, and this comes up with the solution of apatite, which is a material containing calcium, phosphorus, and fluorine, and it gives the chemical formula and the material's geological or mineralogical name. So now we've solved our spectrum. We know that each area that's colored in green is apatite, and then we even take it further. Nowadays, with the internet, we have a huge number of tools available to us where once we know what something is, so for example, we know that this most recent grain was apatite, the others were pyrite and ilmenite, we could search the internet and learn a tremendous amount about these materials. So for those of you in the geological industry, you may have your own databases, but there are some really helpful databases out there. This particular one, I've been working with Tom Mortimer on his vast compilation of many materials, really hundreds of mineralogical and geological materials, and the details, the images, where it comes from, and what the compositional formula is, all available to us there. So once our spectrum library tells it what it is, the world is our internet searchable oyster for understanding truly what it is. And just a couple more examples and some images from the ilmenite and some of the great many number of materials that are available on the search. So this will conclude the formal part of our presentation. Thank you to everybody who has attended, and I'm super happy that we have some a nice group of question and answers. So one of the questions is, what are the EDS analytical ranges for the composition, and how do we know the exact composition? And here, the exact composition with EDS, what we can do is use tools like our carbon coding correction, and that's going to get us closer to the analysis of the exact composition of the material. Also, we can do different techniques. We can collect our spectrum for a longer amount of time. We can collect under various conditions and get our concentrations values that are optimized for them. Generally, EDS analysis will work on materials above a couple of weight % and give you a good target concentration range to help you solve your compound formula. Let's see, yes, is CompoMaps available with the EDAX team software? Great question. CompoMaps is a function that EDX has had for a really long time. It's been in our Genesis software, it's been in our team software, and we've really revamped it and revised it for our Apex software, and we've put it front and center with our Apex software because of the great value. But the answer is it truly is available in team software, and so then you're able to rebuild your maps with net intensity, weight percent, or atomic percent concentration. You could also do the live net mapping as we saw here. Yes, next question is, does the team software work like the EDX Apex that you're describing? And yes, much of the algorithms behind the scenes is similar. So the end result is going to be similar. Of course, there are different buttons and different tools, and some of the algorithms are refined for data handling during collection. But yes, the end result of the team software output is going to be very similar, if not identical, to the Apex software. Question. Yeah, good question. When using the search filter, does it matter what elements you identified in your original matching spectrum? If you fit carbon in the matching spectrum and don't in the unknown, does it matter? Great, great question. We've got two different methods for spectrum matching, and that is chi-square based on spectrum and chi-square based on concentration. And I think I've pulled up this slide. I hope you could see it. So this is the two different examples here. And in this particular example of the pyrite, I think one of them, the one on the top, matched at a lower number. I think it was 70 something, whereas the one on the bottom with the concentration method matched better with an 84% fit. And so to answer your question specifically, you do not need to have the same element list. If you use the spectrum match, the match by spectrum, it's just looking at your x-axis and your y-axis, so your peak energies and your intensities. Doesn't matter if you identified it, doesn't matter if you have identified it incorrectly, doesn't matter what your ID is. You can just match based strictly on the spectral fingerprint. Really, it's the channels, you know, the intensities of each channel or EV bin in your spectrum. And so also to answer the second part of your question, if you fit carbon in the matching spectrum and don't in the unknown, that's okay when you do the concentration method. So if you match based on chi-square on concentration, you could have the carbon in there but do a carbon coding correction and get those numbers. So you have the ability to fine-tune it for elements that you have or don't have in your sample. So concentration method, you could leave elements out and then just do the match based on what elements you do identify. Another good one. Two questions. First, can this technique be combined with SEM EBSD in the area which you are interested in? And yes, it can. Boy, that would be a great next step in the analysis, wouldn't? So we can see the phase, or what we consider, you know, in a multi-phase sample. I'm talking about grains and phases or compounds. But in EBSD, we don't look at the atoms themselves. We look at the arrangement of atoms. And so I'm always having fun with my EBSD colleagues on the definition of a phase. So from an EDS perspective, a phase is the types of elements present and the amount of those elements present. But from an EBSD structural phase standpoint, it's the arrangement of those atoms into a crystal form or a unit cell that defines the phase. So yes, we can do EBSD of that material. Is the software would there be extra components? So you would need an EBSD camera and the EBSD software, and that's an easy enough addition to most all of our systems. Next question is how to correlate the color level with the intensity in a quantitative way. Exactly right. I mean, when we look at a quant map, you know, we're looking at colors, and it's you know, we can't really tell 10% of a color intensity or 40% of a color intensity. So we do provide that marker bar on there, and let me pull up one example of it, and hopefully you can see the slide now. So in this example here, we see the CompoMap on the left and the slider marker on the right, and you can see those numbers. This particular map is the net intensity, so we're just looking at raw peak counts. If we had pulled up the slider for the weight percent, for example, we might see like between 40 and 100% that we could pull out. So we could actually adjust those red tick marks next to the histogram and extract out or select those specific targeted areas. So if you wanted to say, you know, show me every pixel that contains phosphorus between 20% and 40%, then we would just select those sliders, and it highlights on the image. You can't see it here, but it colors it a different color to let you know which pixels you've selected by that. And again, once you've extracted that spectra, you could do your concentrations and reconfirm that. Got a comment, thank you, and thanks back to you. How many minerals are included in the spectral library? So our mineral library is the 53 mineral library, but always growing, and we have some nice budding partnerships with some of the companies mentioned here and referenced here, and also available on your widgets. You should have some links to them. And so our mineral library is always growing. We also have a materials library, and in combination there are about 150 minerals and materials in the library. So, but again, always ability to grow. Apex, a question about the Apex software itself, and Apex is our latest generation of software package, and definitely talk to your local contact or send me an email afterwards, and we could talk about what the options for Apex would be for you. It's super cool. The last couple of weeks I've had a lot of fun with all this data. I've used it very intensely, and we just had a blast. How long is the mapping time to collect this CompoMap with high resolution? Yeah, so this one about 45 minutes, and that's because I upped it to a 512 by 400 pixel res map. Each frame takes about 30 seconds, so each pass is about 30 seconds. So we collect frame by frame and then add them on top of each other, and I did that for 45 minutes. I think most of the display was complete at about 10 or 15 minutes, but of course for the presentation I let it go for longer. And with drift correction, then you don't have to worry about your image, you know, becoming fuzzy or moving. Latest software for team is something like 4.5. How much of such chemically resolved phase separated interface elemental concentration correlated with the accuracy of, say, atom probe? Very good question. If you are fortunate to have an atom probe, I suggest that you use your atom probe to truly define your composition. Or APT, atom probe tomography, is one of the best techniques for analyzing atom by atom. It's a very complementary technique to EDS and to EBSD. And so where EDS can give you a large area and the overview of your general composition with plus or minus a few percent, the atom probe tomography is going to give you the exact number of atoms. So it doesn't get much better than that, than counting atom by atom. Okay, and review of our minerals and materials alloys is, in fact, yes, about 150 materials, large and growing. So any of you who would like to contribute to growing that library, all collaboration is welcome. As it is, I'd like to thank our partners who have been super helpful to that end, Tom Mortimer, and also the group at the Standards, SPI Standards, has been very helpful. Yes, and let's talk about how we can get EDX, your EDX system upgraded with CompoMaps. So that question just came in. Thank you. Please send me an email afterwards if you have any follow-up questions. I will do my best to get back to you in a timely manner, and also involve any other team members from EDX who may also help you. I'd also like to thank our organizers, our marketing group for the great promotion, and our coordinators for carrying off such a successful web session. So with that, thank you to everybody who attended. It is a pleasure doing lots of fun work with new data and great software features, and thank you for your time. Have a great day.